All right, welcome to another exciting episode here of AP Chemistry at Spain Park High School. Today is Tuesday, January the 23rd. And if you are enjoying these very exciting videos, feel free to subscribe to this channel and hit that like button. All righty, here we go. Today we're going to be talking about just doing practice problems on thermo. So we went through yesterday and talked all about the theory and just kind of outlined the whole unit. You have the notes. Now I want to go through these practice AP questions top to bottom and just kind of see how they all just kind of flow together and make sure that we can do this. So if you have your Chromebook, you can get it out because this problem I think is in the packet that I put with one of your assignments. There is with all the 2010, I think I put the whole packet in there. But here's 2015, and Raul left, but this is why we need to get recycling, because the number of aluminum cans that I go through generally.
Wait, where's Raul? He's sick.
Yeah, he's sitting next to this ocean. No, I'm just kidding. I just can't let it go. You know? Yeah, maybe he is. Yeah, and Stanford, and Sandland. All right. So, aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. Okay. Calculate the amount of heat needed to purify 1 mole of aluminum, originally at 298, by melting it. The melting point of aluminum is 933. The molar heat capacity. What does that mean? The molar heat capacity.
Amount of
specific heat measured moles.
raise 1 mole.
I don't want this color green. Too hard to see. So if I'm looking here, we're going to start with aluminum as a solid, and then we're going to melt it. So we've got to go to here. Is there somebody at the door? Oh no. So we're starting here at room temperature, 298. Okay, we're taking it up to here, which is 933. So we have, how many Q's do we have to solve for this? 2. When there's a temperature change, how do we solve for Q? No. Say that again? MCAT. Okay, so remember, if we go back to our heating curves, we have this in your notes. We had the 5 possible Qs. You go from solid to melting to liquid to boiling to steam or to gas, right? This case, we're only going solid to melting. So here, Q is going to equal MCAT. So, but when it's melting, how do we calculate Q? The heat of what? The heat of fusion times. Okay, so look at our units. Okay, the heat of fusion is kilojoules per mole. But I want the heat. I want kilojoules. So what do I need to multiply that by? Moles. So since they're giving you the molar heat capacity, kilojoules per mole times moles is going to give you kilojoules. Joules. Now, notice that too. Joules, they love to do that to you. And kilojoules. If we're going to add them, we got to make sure we're adding apples to apples. Okay? So pay attention to those units. This is joules per mole K. So what do I have to multiply this by? I have to multiply it by moles and K. So we're going to use MCAT, but it's going to be moles times the molar heat capacity. Okay? Pay attention to the units. The units drive it. So see if you can finish it from there. Just A. I have another 2015 in here somewhere. yell at me back. I'll be right back.
Get the ring. Oh, you think? Dude, there's so much mayonnaise. Yes, please. Dude, no way. Nah, get something.
Let me take a bite.
No, get something.
I'm not just drinking mayonnaise.
No, get like a cheese or
I
something.
don't have food. That I can have.
This might have to be handed out in kind yeah.
Bro, how much is that? Well, he does, but I'll wait.
You can hear us right now.
You're a damn
Mr. Hobbs is a dingus.
Wait, bro, we should have left his lunch.
Wait, yeah. Wait.
Oh my
If you
god.
checking out, why did you have lunch?
Yes.
Yeah, you can be at home.
25.
I'm so lethargic. No, we need to stop the slander on my name, bro.
Is that you?
Those are old.
No, not the mayonnaise. I need the cheese in it. Why are you squeezing out the mayonnaise?
Do we have an answer? Yeah? Okay, so what do? We're gonna go, okay, so we're gonna take, how much? We got 1 mole. Okay, so delta, we'll calculate the amount of heat, we'll just say delta, well, let's just say big Q, QT. QT is gonna equal your moles, 1 mole, times what?
635
Well, before then. It doesn't matter the order, but
24.
24. Now again, are we gonna change, we're gonna keep everything in joules? Are we gonna change this one to joules, or are we gonna change that to kilojoules? You wanna do it at the end when you add it up? Okay, that's just dangerous. But 24 joules per mole, okay? Now times what?
635 Kelvin.
Which is gonna be really your 933 minus the 298, just to be, you know. And what did you say that comes out to?
15.24.
What does that come out to? No, this number right here.
635.
635, okay?
Stop using out the mayonnaise.
Okay, then it's gonna be plus, what?
10.7 times
1 mole times 10.7 kilojoules per mole. Now again, notice how the units, this is K. K is gonna cancel, mole's gonna cancel, leaving you joules. So what does this come out to in joules? Say it loud enough for an old man to hear.
15,240 joules.
240 joules plus 10.7 kilojoules. So we just move the decimal here. I can just say that this is going to be 15.2 kilojoules. Okay? And then plus 10.7. So that's going to be what, 25.9?
Yes, sir.
Am I doing everything right? So I'm going to get 25 point, we'll just say 9, and 940, we'll drop that off, kilojoules. So that's the amount of energy it's going to take just to melt 1 mole of aluminum. Okay, so you always remember, if you're dealing with just heating things up, melting, I always kind of at least visualize or write this out, kind of like this, to know where am I starting, where am I ending. Okay, so look at the words, see how it's worded, you know, in terms of calculate the amount of heat needed to purify. And they tell us purify by melting. That's kind of the key. Okay, aluminum first, okay, to get rid of the impurities. So we're looking at Keith because they don't really say how much to melt it. They're going to purify it, but the prompt tells you that that's what they're going to have to do, is to melt it to get rid of the impurities. Okay? Now the equation for the overall process of extracting aluminum is shown below. Yeah, in just a second I'll pass those all out. Alright, so now it says, which requires less energy, recycling? Justify your answer with a calculation. Okay? So now this is 1675 kilojoules per mole. Okay? How do I figure out how much energy it takes for 1 mole? Okay? Well, we have kilojoules here. We're comparing 25.9. How much is this going to take? And how do we know? What are the units here?
Kilojoules per mole reaction.
Kilojoule per mole reaction. What does that mean? Which part of this are we interested in?
2Al.
The 2Al. Nothing but the bottom of the bucket. Okay? 2Als, right? So it takes 1675 per 2Als. How much is it? How much was this one? Per what?
1.
1. So how do I find out 1?
Divide by 2.
Divide by 2.
Wow.
Okay? So you just simply go for B. It's simply going to be 1670. Q is going to equal 1675 kilojoules per 2 moles of aluminum is equal to 837.5 kilojoules per mole of aluminum. This is for melting it. This is just this is the way that you get purify aluminum. This is called bauxite. Okay, that's the raw material for aluminum. That's when they mine it out of the ground, and most of that comes from Russia. It was kind of interesting that in Baton Rouge, when I first moved there in the late 70s, I was driving around and they have an army ammunition dump or plant, and they had this big mound covered in grass, you know, but big mounds of dirt. But you know, so I'm thinking, man, they got all kinds of machine guns and bullets and hand grenades and grenade launchers and all that stuff in there. Then I found out, nope, it's bauxite. Because if there was ever a war with Russia, we need to make sure we have a stockpile of the bauxite so we can have aluminum to make the war machine. And so they stockpile it because we need to be able to have the raw material in order to be able to get that. But they purify it through this reaction, and they're not even saying how they do that. But you can get pure aluminum from this by this reaction. It takes this much energy total to get this aluminum from that. But the equation for all is this: which requires less energy, recycling or extracting? Well, obviously, which one takes less energy? Recycling. Well, not just a little bit. Okay, 25 kilojoules to melt it and purify it, what's already made, versus 837 kilojoules to get it from scratch. Okay, that's why we want to recycle aluminum cans. If you want to conserve energy, okay, you also conserve space in a landfill, and that's the biggest issue with trash is we're running out of landfill space. Okay, because as much as we think, oh, it's going to decompose and all that, it doesn't. There's a guy called Dr. Dirt. He does archaeological digs in landfills, And he's gone in and dug down deep and found newspapers from the 50s with hot dogs right next to it. Okay? They hadn't decomposed at all, because in order for decomposition to occur, you gotta have oxygen. So if you ever do a compost pile in your backyard, one of the things you have to do is you have to keep going and turning it to expose the different parts to the oxygen so it can actually decompose faster. When you just cover it with dirt and compact it, the stuff doesn't decompose. So it's not a matter of, plastic or paper, all that. The paper is going to decompose and plastic's not. The reality is plastic compresses better than even paper does. Takes up less space. Problem with plastics is it gets into the rivers and streams and then causes problems there. Yeah, it doesn't decompose, but the newspaper and the trash that you're putting in doesn't decompose either. But if we can recycle our aluminum cans, our tin cans, and do all that, we save all that landfill space. Plus, it takes tremendously less energy in order to be able to do that. So it's a win-win all the way around, no matter how you want to look at it environmentally. Okay? Which is why, Raul, if you're watching this, actually, it's not his fault. I called the company and they said they were going to call me back, and they never did. They've had all kinds of negative press. I've been watching the news, and the trash company's been on the news negatively about 3 times in the past couple of months, as far as their service. All right, so that's one. That's more of a stoichiometry type problem, just using the units. Everything's given to you. You just have to know this. But it's also a heating curve where you have to know that to melt something, you have to both warm it up to its melting point and then cause that heat of fusion to make it melt. Okay? This was 2015. This would be a 4-point. This would be considered, this was a question number 7. This is the last question on the test. This would have been a 4-pointer. It would have been 2 and 2. You should be able to do this in about 10 to 12 minutes. All right, you breaking them up?
Yeah. Well, it's heavily.
Yeah. Okay. Well, the super copier was out of Staples. Copier can staple and hole punch.
This is looking good.
This I think passed down. Should be front back. You should have several pages. Okay? Thank you. Now, if you want to, you can take that stapler and then staple all those packets. If you're bored. It'll be a little loud. It won't. That stapler's not loud. Okay, let's look at the next one.
Pops loves having apprentices.
Turn it over. Turn that 15 over, and you get a 16. Ooh, it does two-sided too. Ooh. All right. So a student designs an experiment to study the reaction between sodium bicarbonate and acetic acid. That's baking soda and vinegar. That's your volcano reaction. The reaction is represented above. The student places 2.24 grams. So if I'm doing this, I'm going to go and I'm going to say, okay, I take 2.24 grams of this. I like to just write it right above it. And add 60 milliliters of 0.875 molar. Student observes the formation of bubbles, okay, and that the flask gets cooler as the reaction takes place. So which part is going to be the bubbles? Okay, so this is your bubbles. And what does the fact that the flask gets cooler tell you?
Endothermic.
Endothermic. So I'm just reading this and I'm just picking out all these clues. I haven't even looked at what the question asks. I'm just looking at the context clues from the question. just breaking it down. What do I know? What am I going to see? So I can just have it kind of get through all the fluff and just kind of see where we're at. Identify the reaction as an acid-base reaction, a precipitation reaction, or a redox reaction. Now, we haven't done acid-base or redox or any of those, but is it a precipitation reaction?
No.
Because what's a precipitate?
Solid.
A solid. There's no solid form. So I know it's not a precipitation reaction. Anybody have a clue what you think a redox reaction would be? The charge is changed. The oxidation states change. Okay? But we can see, okay, acetate, this is really just a double replacement reaction, but we're making H2CO3. But remember that H2CO3 always breaks down into H2O and CO2. So it's really a double replacement reaction. Okay? Sodium is going with acetate. Hydrogen is going with the bicarbonate, making H2CO3. But then that breaks down into H2O and CO2. But if it's a double replacement reaction, that's the only type of reaction that is not a redox reaction. That's the only one where the ions just swap. It is an acid base because, and we'll cover this more later, so this isn't something you'd be tested on in this unit. But it's, remember, acids donate hydrogens, bases accept hydrogens. Remember that from Chemistry 1, the Bronsted-Lowry definition? Acids donate, bases accept. So the hydrogen is getting donated and the bicarbonate's accepting. So it is indeed an acid-base reaction. Okay? We'll do that. That's what one of our last units. But that's how we would know that. So we should be able to eliminate it down. You know it's not a precipitation. Okay? Redox, charges change, but double replacement reaction is the only one that is not a redox reaction. What's the limiting reactant? Well, do you guys remember how to do limiting reactant?
So for like an AP question, it says like justify your answer. How would you word that?
Okay, I would word it by it is an acid-base reaction because the acetate donates the hydrogen to that. Because that's what acids do. Now this would be a long question. This is going to be a 10-point question. And this gives you about 20 minutes or so in order to be able to do this. You're going to have 105 minutes to do 3 long questions and 4 short ones. Okay? So usually it's about 20 minutes each on, for the long ones. That's 60 minutes. Okay? And then you have, another 12 minutes or so for the 48, so that gives you 108. But so you really have a little bit less than that, about 10 minutes. Really, if you do 18 minutes on the long ones, just you can't get too bogged down. If you don't know it, skip it. Run out of time on the ones that you don't know how to do. Make sure you have time to get to all the ones you do know how to do. All right. So how do we get limiting reactant? Does anybody remember?
Get a moles on both.
Okay, what's the ratio between them?
1-to-1.
1 to 1, so whichever one you have the fewest moles of, right? So see if you can go change the moles. No, it should be where the hole, staple on the top left, where the holes are. But it should be, we want to start with here, you start where you're going by.
Wait, it's not 26.
And you should be about done.
Oh, really? Weird. I hate units.
I gotta switch up my numbers. Oh, I divided. Wait.
Thousand.
Wait.
Thousand.
That's sentence. Sentence. So what was it?
So Grayson, what's the molar mass of sodium bicarbonate? 84. Everybody agree with that number?
Six.
But hey, let's go with a little bit more sig figs than just 84 though. What? It's 08?
0-1.
84.01?
Yeah.
So that's pretty close. So 84 and 84.01 we'll live with. Okay, so what does that come out to? 0.0267. That's 3. That's enough. That's moles. Okay, so how do I change 60 milliliters to moles?
Multiply by the molarity.
You got to use the molarity, but molarity is what units? Moles per liter. So 60 milliliters is equal to how much?
0.06 liters.
And so, but it's 60.0. So keep those zeros. So that's liters times the molarity, 0.875 moles over 1 liter. Okay? So we got to be able to, you don't have to show work for the conversion. You can just do that in your head. That's one that should be common knowledge by this point. Dividing by 1,000, just moving the decimal 3. And so what does this come out to?
0.0525 moles.
0.0525 moles. And I need to label NaHCO3, H2, HC2, H3O2. So which one's my limiting reactant? Because we have, and you have to, based on the identify, justify your answer with calculations, and so you just say because it has fewer moles, it's the limiting reactant. Okay? So that's your calculations. Now, we haven't really covered this, but I think this is fairly common knowledge, which is basic chemistry knowledge. The student observes that the bubbling is rapid at the beginning of the reaction and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of collisions between reactant particles. Go ahead, Luke.
Well, as there's less things, as there's less collisions, because there's less particles to react with, the reaction's just going to slow down as it just pretty much comes to zero as there's no reactants.
Okay? Somebody else say it in different terms. Go ahead.
There are less and less bubbles as the reaction continues because gradually over time the reactant depletes, therefore causing it to quit.
Okay, but they're causing it to have what? In terms of the answer, in terms of what they're asking for, in terms of collisions. So as the reactants deplete, there's going to be what? Fewer collisions. So we want to use the term that they're asking about in our answer. Okay, so over time, however you want to say it, as time goes on, there's less and less reactants, and so therefore the collisions between reactants become less and less, and the reaction slows. But again, here's in terms, it says the rate in terms of collisions between reactants, so we need to make sure we use that term in our answer. And again, that's our next unit is reaction rates. Oh, a lot of people are going to be out Thursday and Friday for different reasons. I think we're gonna do the lab tomorrow. Okay, because, so many people had said they're gonna miss for various reasons on Thursday and Friday. And especially in sixth period, I guess.
The lab gonna go into AO.
Yes. Oh,
Battle of the seniors tomorrow.
battle, oh, that's right.
Maybe we should not have a lab. That's like
Y'all
the
just
Dodger
do
Bowl
it.
when they miss basketball.
We might be able to get it done in a class period, but I don't,
What is it?
you guys make life so complicated. That's tomorrow. Oh, that's true, that's tomorrow.
So basically no lab.
They've totally destroyed AO.
Yeah.
It's today's freshman and sophomore.
Yeah, tomorrow's juniors and seniors.
Wait.
Alright, okay, I'll try to modify the plan, we're just gonna see here. I may just have to video the darn lab and watch people watch it on video. Alright,
Wait, let's not have a lab.
not y'all, I mean, the people that are here will do it, but the people that miss won't get to do it. Alright, so now let's look at D, okay? In thermodynamic terms, this is where we're now getting into this unit, okay? A reaction can be driven by enthalpy, entropy, or both. Do not say an answer out. Considering that the flask is cooler as the reaction proceeds, now I'm surprised that they said it again, but what drives the chemical reaction between the two? Answer by drawing a circle around one of the choices below. And then the part 2 of it is justify your answer.
You can draw a box when you get wrong.
No. But if it says draw a circle, doggone it, draw a circle. But it doesn't matter, as long as you identify which one, the graders aren't that big.
So
Okay? So hey, we need to be able to justify your answer in number 2. Have we already all done that? Y'all are just kind of looking at me. Circle it, but then justify your answer in words. That's what the II means. In terms of delta G. Okay, so you have to do it in terms of delta G. So obviously delta G's got to be in your answer.
So this reaction would be unfavorable to the input.
Well, that's what you're trying to figure out.
Wait, what is delta G again?
Gibbs free energy. Delta G equals delta H minus T delta S. Greenhouse table. No, they're gonna get drunk. I start next week back. I always tell myself 3 weeks. I was only sick for a couple of days.
It's fine after.
so cool. Are you gonna get bullied off the ball by a freshman? Okay, I would, but I never did. Sam would also. Actually, would you ever think about that? Yeah. Sam's pretty amazing. I can't even tell it looks cool.
Is this an extra one?
No, it's mine.
All right, so what do we think? Is this an entropy driven, enthalpy driven, neither or both? Entropy. Now, first off, what's the sign in terms of delta G then? What's the sign of delta G going to be because the reaction occurs?
Negative.
Negative. So in order for delta G to be negative, delta G is equal to delta H minus T delta S. Okay? So in order, what's the sign of delta H?
Positive.
Positive. And what must be the sign of entropy?
Positive.
Positive. And how do we know that it's positive?
Because the reaction occurs.
Well, but just looking at the reaction, how do I know it's positive? Because I'm increasing moles of gas. I'm going from solids and aqueous to gas. I'm going from 0 moles to 1 mole. So I know that entropy is increasing because moles of gas is increasing. You can always just look at moles of gas. Is it increasing or decreasing to determine whether entropy is increasing or decreasing? If you have more moles of gas as products, it's a positive delta S. If you have fewer moles of gas as a product, you go from a gas to a solid or aqueous, then it's going to be a negative delta S. If it's the same, the delta S is pretty near 0. Okay? It's only gas. You only look at gases. Compare gases reactants to gases products. If gases increase, entropy is increasing. If gases decrease, entropy is decreasing. It's that simple. Okay? Just look at moles of gas. So I know that entropy is also positive. So, but I know that because, how can we answer this then in terms of delta G? What did you guys say? Because delta G must be negative, and we know delta H is positive because it gets cooler, it's endothermic. Delta S must be positive in order for delta G to be negative. Positive delta H is not favored, whereas a positive delta S is favored. Therefore, this is an entropy-driven reaction. You need to say positive is not favored, it's not thermodynamically favored, whereas a positive delta S is thermodynamically favored. Therefore, it's an entropy-driven reaction. And I would write the equation out. I would maybe do something just like this as part of your explanation.
It's all on the test.
This equation is on the equation sheet. Okay? Now, the rest of this isn't really thermo, but it's good. Now, F is acid base. We're not there. You can just circle that, come back to that later. Okay? This we've already done. So this is a good review. See what you think on this one. Just reading it. We may have already done this as a practice problem. I only see one. Okay. It's a start. Notice what I have underlined.
Carmen, did you just listen to
What concept is this question asking about? Resonance. Resonance. That's the key. Just most individual parts are going to ask one concept. You got to figure out what that concept what they're asking about. This one's a resonance. They also tell you has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the third is longer than the other 2. They tell you the hydrogen atom is bonded to one of the oxygen atoms. So they kind of tell you what's going to happen. So you have the carbon, you have oxygen, oxygen, oxygen with one of the hydrogens there. Now we count our total number of electrons. We have 1 plus 4 makes 5, plus 18 makes 23, plus 1 extra makes 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Are we done?
No.
What's the problem?
C doesn't have 8?
C doesn't have 8, so what do we need to do? Double bond. Can I form a double bond with this one?
No.
But I can pick either one of those, right? As soon as I have a choice between the 2 oxygens, that tells me resonance. So, and that also is the key here, they give you kind of a clue or diagrams. That, hey, maybe there's going to be the resonance structures. So we're going to make a double bond, doesn't matter which one. And remember, if it's an ion, you put it in brackets. So you do a double arrow. So I know then that the carbon could form the double bond here instead. And you have to have your lone pair. You have to have your lone pair. Somebody missed some points on the semester exam because of lone pair.
Again?
No, I mean, I think that was you, right? That forgot to put your lone pair
On the test, but I remember
on the
the
test?
exam.
Oh, on the exam? Okay, I just knew there was one.
Yeah.
Okay. All right, at least you learn from your mistakes. That's good. Okay? Now, why does it say that 2 of the bonds are the same and one is longer than the other?
Because one's kind of getting full.
Because
The resonance one is shared.
These two are going to be identical. What's the bond order going to be on these? About 1.5. Remember, the higher the bond order, the shorter the bond length. So a double bond is shorter than a single bond. A triple bond is shorter than a double bond. So here, these two are at 1.5. They're going to be this identical because that pi bond is being shared equally by all. Okay, so these two are identical, but it's 1.5, so they're going to be a little bit shorter than the single bond here. All right, so they're kind of giving you that clue in there on how things go, but they're really asking about resonance to know that, hey, in a resonance structure, remember the shared bonds is really that pi bond that's shared equally by all. And so as a result, they're going to be identical in strength, length, characteristics in every way. Okay? And then F is an acid base. We don't know how to do that yet. All right. So that's just some practice, and we're going to continue through this packet tomorrow. Okay? Y'all have a great day.